welcome back to the session 2. Here where we'll hear some perspectives from some of the Task 13 experts who contributed to the report. Our first speaker is Nicholas Rydell Lundskar, if I pass, from Denmark, and he's going to be talking about optimizing and best practices for monitoring bifacial track systems. And I'm sure it's going to be a very entertaining talk. So thank you.
Thank you, Josh. And yeah, it's really exciting to be here going into the details of this report. So I'm going to be talking about general best practices for monitoring the performance of bifacial track systems. And what I talk about today is really a subsection, or most of the details that I'll talk about today are included in a subsection of the report that's already been mentioned. I think Josh already went over this outline. There's 6 sections, and what I'll be talking about is in chapter 3, where we talk about instrumentation best practices for bifacial track systems. So in terms of monitoring of PV performance in general, the sort of industry's best document that we have is in IEC 61724-1. It really codifies a lot of the industry's best practices. In terms of bifacial systems, so the standard breaks it down into Class A and Class B systems. I'll be talking about Class A, which are geared towards utility scale. And when we talk about bifacial, we typically have to discuss rear radiance. And the standard gives you 2 options for that. You have option 1, where you can measure horizontal albedo. If you do that, you'll need to supplement that with a diffuse irradiance measurement to help your modeling, view factor modeling, to get to rear plane of array irradiance. Or you can measure rear plane of array irradiance directly. So it is a more straightforward measurement, also because in densely packed PV parks, it's typically pretty challenging to find an open area sufficient enough for unshaded albedo measurements. The standard does say you can measure rear radiance with bifacial reference modules and cells, but there are just a lot of details lacking in the how. So our goal with this section in the IEA report was to sort of supplement areas or gaps where the IEC standard is missing. So today I'm really going to focus on rear irradiance and a little bit of front side irradiance. But if you're interested in module temperature, albedo measurements, and even wind speed direction measurements for bifacial track systems, check out the report. So this graph shows how the quantity of different sensor types scale with PV plant capacity for Class A systems. And what you notice in the difference between the orange line, which is rear irradiance and back of module temperature sensors, versus the blue line, which is all other sensors, is a factor of 3 more. So the standard tells us what kind of sensors we need, how many you should have, but it doesn't say exactly where you should be placing these sensors. And it's not really the standard's job to do this, because it would be really difficult to provide general guidance on sort of how to mount sensors for every structure type. But since we're going into the details of tracker systems, then we have a chance at providing some pretty specific guidance. Yeah, so just jumping right into the conclusion here, and then I'll go into the details of how we got here. But this is our main conclusion for a recommendation for measuring rear radiance on bifacial trackers. So the frame B here shows a close-up of where we suggest to mount small area sensors like pyranometers or reference cells. It's kind of where your intuition might have told you, halfway between the east edge and the torque tube, and then another sensor halfway between the west edge and the torque tube, and then average those 2. The top A frame there shows a zoomed out view that shows roughly how far away from the nearest north or south edge the sensor should be to avoid edge brightening. So these results are applicable to 1-in-portrait and 2-in-portrait systems. If you have a 2-in-portrait system with a torque tube gap, a light gap there, the results are a little different. You should actually place those sensors a little bit wider or closer to the edges. And so we didn't make these recommendations up out of thin air. It's actually backed up by a lot of studies and literature, some of which are listed here. So going into the details of how we got to that suggestion, one way you could approach the problem is with ray tracing. So in this particular work, we did ray tracing simulations using bifacial radiance. We simulated 3 different tracker types, including 1P, 2P, and 2P with a gap in 9 different climates. And then these climates were selected to represent sort of a range of solar resources, albedo, and solar geometry, sun paths. And what you're looking at here in the graph is results for one particular location in Spain of a 1-in-portrait tracker. The orange dots are showing you the cumulative rear plane of array irradiance for 20 points on the backside plane of array. This is for a center module. And then there's also 3 positions that we simulated on the torque tube. So the sensors would be essentially parallel to the plane of array, but they're displaced by about 15 centimeters. 1 in the center and then 2 on the north-south edges. And then in this case, the south-facing sensor is what, I don't think the standard calls it this, but it's been referred to as an outboard sensor, where that location maybe isn't representative of the whole array, but it is free of shading obstructions or structural objects. So what you're looking at is from the west and the east, you see a brightening effect there, and then towards the middle where the torque tube is, there's more shading there. The horizontal dashed black line shows the average of all plane of array measurements on the back, and then the vertical dashed lines show where the model values intersect with that line. So that's what we're saying is really the best position to select, is something that represents the average and actually not the minimum. This plot shows the error as defined by the difference to the spatial average. So the difference between each of these individual points from east to west, also the torque tube on the back of the array, relative to the spatial average in different climates. And what you see is that there's no single position on the back of the array that can minimize this error lower than, say, 7 to 10%. Interestingly enough, the torque tube actually has gives the best match to the average, but a single sensor on the torque tube really isn't able to capture sort of diurnal variations in back of plane of array irradiance that the array does see. So what we do see is if we start to take one or more of those locations, so there's a lot going on in this plot. Let me walk you through it. It's a variability plot showing, so the colors are different tracker types, 1P, 2P, and 2P gap. And then the frames are the error that you would observe with different sensor positions and combinations of them. So the 3 frames on the right show you the error over 1 year for sensors, a single sensor on the torque tube, single sensor on the west, and a single sensor on the east. So yeah, that's that 7 to 10% error I talked about earlier. But if you simply average 2 of them, one on the east, one on the west, your error, again, defined as a deviation from the spatial average, is about 2%. And if you keep this in perspective with the fact that the front side plane of array irradiance is about an order of magnitude higher, this really has a minimal effect. If you add a 3rd sensor, so that's the 2nd frame from the left, on the torque tube, for example, you don't decrease the error. So this suggests that the IEC's recommendation of 3 times rear irradiance sensors could actually be reduced to 2 times. And then you could potentially say the 3rd one is optional if you wanted to measure edge brightening effects on the north or south end of the torque tube. Oh, and we did some sensitivity analysis on this. So we varied the tracker heights, varied the GCR, albedo, all within sort of reasonable tolerances of what you might expect. And we found that the best sensor positions don't change by more than 5 centimeters, which is about half a cell. This is a real practical sort of zoomed in image of how you might do this measurement on a tracker. This is a 2-in-portrait tracker. So the sensor in this case is mounted to the transverse beam, also called a purlin. There is also an extra bracket on this purlin to help with the cable management. So you can also see there's actually a back of modules temperature sensor there, right adjacent to the pyranometer, and that helps us minimize shading due to the cable. So earlier I mentioned that, 3 to 5 modules. So is it 3, is it 4, is it 5 modules from the nearest edge? Chris DeLine at NREL recently published a paper that includes a table of minimum modules that you need to go from the nearest equator facing edge, all based on pretty simple trigonometry, but that's really helpful. But this one's 5 modules away from the nearest edge. And of course, there's an equivalent sensor on the other side of the tracker, not shown here, but those two would be average. So that's rear plane of array irradiance. And I think when we talk about bifacial, we oftentimes get really caught up with rear irradiance measurements and modeling, but we can't forget the importance of front side measurements and the accuracy of those. So our report also has some recommendations for where to place front side plane of array sensors on trackers. It's based on a work from Kip and Zonin, who did, again, bifacial radiance ray tracing to really identify the spatial average of the front side plane of array irradiance for a center tracker. And what they found was that there's areas that are brighter, areas that are more not as bright as others, to the tune of plus minus about 2 or 3% relative to the average. A lot of this is due to sort of shade masking from the row preceding the tracker. It's akin to the same effect exists in fixed tilt systems. So if you place the pyranometer on the bottom of a fixed tilt system on the front side versus the top, the bottom would have more shade masking from the preceding row. So in this case, it's just the view factors are changing, say, dynamically over the course of the day. And coincidentally, those green bars in the center tracker there actually really overlap exactly with our recommended positions for backside sensors. But in this case, you would only need one or the other position. I will add to this. So we've done a lot of validation of the rear irradiance measurements, but I think this is still lacking a real comprehensive field validation. So that's an open task for the community. Just to summarize, I think we're going to see a lot more bifacial trackers into the future, and we hope that our report is going to help the industry design better bifacial track systems. There's a QR code here, if you haven't scanned it already, to the report. And the question about where to place your backside sensors on trackers, it's kind of where you might have guessed. Halfway between 2 of them, placed halfway between the torque tube and the east-west edges. And if you do that, we think you're going to observe about a 2% deviation to the spatial average rear array irradiance, which again will have minimal impact on total irradiance. So thank you. Here's the QR code again. Thanks.
Great, thank you. Thank you. We'll do questions at the and discussion at the end. Our next speakers, Madalena Bruno from Fraunhofer ISA in Germany. And she's doing a PhD thesis on tracking algorithms and optimization. So we're hoping to see some of the work that we included in the report, but also maybe some hot off the press results research. So take it away, Madalena.
Thank you so much for the introduction and thank you for having me here. As Josh said, I want to bring some field insights, some concrete data from our experience on diffuse tracking performance. So we already seen all of these, but by today, trackers represent 60% of the market share, and they can be controlled by many different tracking algorithms. If they are based on exclusively the solar position, they are called astronomical or true tracking. However, most of the systems have backtracking, which is an evolution of astronomical to take into account the GCR, so the ground coverage ratio, and to minimize the row-to-row shadow, especially in the morning and late afternoon. An evolution of this is the slope-aware backtracking, which is an adjustment for uneven terrain. And then we have the more recent partial tracking, which aims to shade half of the module for recent module technology with bypass diode. A big field of tracking algorithms are real-time control strategies, which also take into account real input from sensors and weather forecasts. And they can be for different purposes, such as address extreme weather events, as we saw also in the session before, which can be wind, hail, and snow response, but also for novel applications, such as agrivoltaics application, and then also for yield optimization, whether this is diffuse optimization or AI integration. So when it comes to weather response, the majority of producers and trackers providers implement this response. However, we noticed through the survey presented in our report a lot of variability, both in the range of the threshold considered, which can vary between 15 to 22 meters per second, which depends on the system type, on the mounting structure, but also on the height at which the wind is measured. But also, as we saw in the session before as well, we have quite a variation in the stow position considered, which can go from 5 to 30 degrees. Also, snow response is quite extensively implemented, and it's based on a deviation to full tilt whenever the snow is detected, and is based on sensor measurement. However, for what concerns the full tilt, it depends on the type of system and can vary from 50 to 60 degrees. A bit of a more advanced response to extreme weather is flood response, which consists in moving to stow position whenever a flood is detected through sensor measurement. And then lastly, we have the hail response, which could be either manual, so based on a manual override of the tracking angle, or can be automized based on nowcasting techniques, so very short-term, very precise weather forecast. And this also relies on the movement to full tilt position whenever detected. Traditional tracking algorithms are optimized for clear sky days, so when the direct irradiation is the prevalent component of irradiation. However, if we have overcast conditions, so we have a majority of diffuse irradiation, then classical tracking algorithms do not work properly, or they do not perform at best anymore. Because the position that maximizing the radiation capture from the sky dome is the horizontal position. In the literature, there are many different studies that try to assess the theoretical potential with claims ranging from 0.5% to 3% yearly. However, there is a lack of understanding, first of all, on the condition at which implement diffuse tracking. So exactly when do we go to stow position? And also there are few field implementation, so, or at least there are few available data to really assess the practical potential of diffuse tracking. So we have a lot of theoretical potential, but then how do we translate this in reality to an existing system? And therefore, to meet this gap and to answer to the research question, we started the Deep Track project in collaboration with Zimmermann PV Steel Group. And here you can see a picture of the system, which are 90 kilowatt peaks installed in the southwest of Germany in Merdingen in our outdoor performance lab. And we divided the system in two portions. So we have group one, which is our control group, which follows a backtracking strategy. And then we have group two, which follows a diffuse tracking strategy. And then we take the string data from the inverter of the string 2 for control group 1, and then from string 8 for the group 2. And then we compare the string data to assess the energy gain. And also the reason to focus only on these two strings is to avoid the area in the middle, which is affected by self-shading, since the two groups are following different tracking strategy. Also, we implemented a quite holistic and comprehensive monitoring system to be able to assess all the weather parameters. So first of all, we have a tracked reference cell for every PV row. Then we have the echo tracker, which is a quite advanced sensor to assess the different components of light. So the global horizontal irradiation, the diffuse horizontal irradiation, and the direct normal irradiation. Then we have a weather station with a precipitation sensor, wind sensor, horizontal reference cell, and then the Sunto sensor, which is a sensor from an Italian manufacturer made of 11 different photodiodes arranged in different geometric position, which is able to achieve the same result basically of the echo tracker, but in a much more concise and cheaper way. So we also have the different components of irradiation from the Sunto sensor. And then lastly, we have the POEA scan, which is a special sensor developed for us from PV Performance Lab, specifically for tracking optimization work. So this sensor is a reference cell and a photodiode on a rotation axis that every minute perform a scan of the sky. So they take a 360 rotation to exactly evaluate at which angle the maximum irradiation is occurring, the maximum plane of array irradiation. So we have quite a broad set of sensor measurements that we want to combine all together. Also, they have different ownership. So we use MQTT to combine them and store them in our own database, as well as integration with weather forecaster. And this will allow to perform real-time optimization and real-time operation of the system. However, when going from theoretical study to practical work, there are always complications. And also, as often happens in the solar industry and in communication between different stakeholders along the value chain, the data exchange is often the first bottleneck. So we had to find a first step, a first implementation of the study, which is based on a more simpler solution, but still it will allow us to evaluate the performance of the diffuse tracking optimization on a longer period of time, and also to establish this condition for activation of the optimization. So basically, we are using the ZimTrack logger and the already integrated sensor data, and then we compute the diffuse ratio based on the readings of the Sunto sensor, so the ratio between the diffuse horizontal irradiation and the global horizontal irradiation. And then based on the value of the diffuse ratio, we take action. So if the diffuse ratio is below 0.5, then also the group 2 is following a backtracking strategy. But if the diffuse ratio is above 0.5, we go to stow position. So the group 2 moves to stow. However, as you may imagine, this comes with some complication and some limitation, because in the current implementation of the algorithm, we, first of all, are using the readings of the diffuse ratio from the Sunto sensor, which is subject to certain limitation. And then at the moment, we do not integrate weather forecasts yet. So this leads to excessive additional rotation time. So here you can see an example of a day with very volatile weather condition, with a diffuse ratio that is changing very often from above and below 0.5. And therefore, the string 8, which is following the diffuse tracking, is jumping back and forth a lot from the backtracking to the store position. And this leads to an increase of the rotational time of 119% for this specific day, which of course it's not desired, and leads to additional wear and tear of the motors. And that is why we are working so intensively on the integration of weather forecasts, because this represents the main asset to achieve or to face this challenge. Also, of course, we are subject to transmission networks and trackers movement delays, as in every tracking system. However, on the positive side, we analyze the performance of the diffuse tracking optimization for a period of time from the 12th of January to the 28th of January. And in this period of time, we noticed that the diffuse tracking was activated 59% of the time, which is quite a big amount of time. And for the diffuse days, the gain from the diffuse strategy ranged from 5 up to 14%. So for instance, here you can see the example for the 19th of January last month. Thanks to going to the store position, we increased the energy gain by 14% on this day. If we look at the whole period, then the gain is of 1%, which seems a bit low, but because we decided to be quite broad with the diffuse ratio for the condition of activation, considering a diffuse ratio of 0.5. So we noticed that there are some period of time in which actually the diffuse strategy is resulting in a loss. So going to store position, it's not ideal because we are losing part of the direct normal irradiation that is coming. However, if we look only at the positive gains, so if we look only at when the diffuse strategy is working correctly, then we have a 2.2% increase, which is an important number, and is also aligned with previous simulated work that we carried out. And therefore, this justified the research effort and the high interest, and finally brings some field experience and some concrete data from our site. Here are all the reference used, and thank you so much.
Thank you, Madeleine. A very interesting talk. Our next speaker is Adam Jensen from DTU in Denmark. And he, along with my colleague, Kevin Anderson, have been doing some work on looking at how to adjust tracking algorithms for varying topography. And so we'll hear some of their latest results in that area.
All right. Well, my name is Adam Jensen. I'm a scientist at the Technical University of Denmark, and I work together with Kevin Anderson, who's not here today. But we've been doing a lot of work sort of on shading and tracking algorithms. So my research areas is solar resource assessment and PV performance modeling. So this is kind of sort of a unique intersection, right? That I care about stuff like shading, right? Solar resources, the incidence irradiance, and of course, what effect that has on performance. And one of the few cases you can actually do something about shading is if you have trackers, right? Because there we have some kind of control over. Of course, with trackers, we get some kind of movement. The very easiest we can do, as Madalena said, is just to do sort of astronomical tracking. Minimize the incidence angle, we get the lowest sort of reflection losses and whatnot. But we have something that's called backtracking, right? And we'll dive into that today, where we kind of rotate them backwards in order to avoid shading. So we're not getting any more irradiance, we're just distributing it sort of differently. And last, we have these different stow modes, and of course also diffuse optimization. But what I'll talk about is going to be just sort of a deep dive into backtracking and why backtracking isn't just backtracking. There's sort of a whole wealth of different methods and different things to consider once you sort of get into the details of backtracking. Here we just have a simple example of two trackers, right? This is probably true tracking, and we see that they're casting a shade. Now backtracking would then be just to sort of backtrack just right where they're not shading anymore. You can see that just sort of thin line in terms of the shading. So we've done nothing to increase the irradiance, right? Because we are sort of in a constrained environment. We've just distributed it now evenly across the trackers. We may even have, slightly higher incidence angle losses because we're not positioned as well. But there's good reasons for why this actually is sort of a practice that makes sense to do. And to see that, here's just sort of what true tracking would be in the very morning for a north-south facing tracker plane, which is sort of the common, right? You start by facing completely east as the sun rises. Then by noon, you're going to be, completely horizontal. And then by the evening, you're going to be facing completely west. Now with backtracking, that's not quite true because in the morning, whenever the sun is the lowest, that's when we're going to have, the longest shadows being cast. So there you would actually start sort of horizontal. And then as the sun comes up, we're tracking more and more into the sun until at some point we reach where there's no shading and we're true tracking. Then for the remainder of the morning and afternoon, that tracking is the same, right? Maximizing for direct irradiance in this case. And then when we come to the afternoon, as soon as we hit that first shadow, then we start backtracking, right? Going more and more horizontal. One thing that's nice about it is that it doesn't cost any extra energy or any extra wear and tear on the motors because, you're probably horizontally stowed in the morning and you're kind of moving in to where you want to start your tracking. And the same here in the afternoon, right? In the afternoon, you got to go back to the morning position. So there's sort of no extra wear and tear on the motors, and there's no extra energy losses. So it's kind of like a free technique in terms of that sense. But let's take a look at sort of why it makes sense to do, and that kind of comes down to the different types of modules. This here is just kind of a conventional module where the cells are connected in series, and we have 3 of those in this case here. So that's kind of what module's been looking like for the past, 20 years or so. Here's sort of the interconnection, right, of that first part of the modules. We see that all these cells here are going to be in series. Now in this case here, when we have shading of the bottom, we have a reduced irradiance on these bottom cells here. Whereas we, have full illumination on these top ones here. When we're looking at the IV curves, right, that's going to affect our current here. So we have the full illumination instead of the top, and then we have what's going to be our IV curve of the shaded. Of course, there's a lot less sort of energy available, so we're going to have a lot less energy sort of available in that. But given that they're connected in series, right, whatever current goes through this cell is going to go through all the different cells. So that means they're all subject to the same conditions, but the IV curves looks different. So that means that you cannot just kind of optimize for the fully illuminated ones because you're going to be sending that same current through your shaded cells. And if we kind of look at the full sort of, picture here of the IV curves, right, we see we're actually getting into the negative voltage in this range. So if we were to just do like a classical MPP tracker, we're looking at, where are we getting the most energy out of the fully illuminated shades will be about on this kink right here, where we have the highest fill factor, running at a current about, 8 amps. But given that we have the shaded one for that case, right, we're running probably at 2 amps. And we're going to be, stacking these sort of IV curves and trying to find an optimum. And if we were to run at these 8 amps, right, you'd be seeing that for that shaded cells, right, we'd be having some very negative cell voltages that are going to be doing some kind of damage. So basically, we're going to end up sort of catering to the cell with the lowest illumination. So even though that, of course, we have an irradiance reduction because of shading, the sort of effect on power, it's much more, it's much greater. It's like an order of magnitude, in some cases, larger. So by backtracking, maybe we get a percentage or 2 higher sort of energy losses because of incidence angles, but we have that same irradiance just distributed evenly. So all of our IV curves are going to be looking identical. They're going to be probably shifted down a little bit because the irradiance is less per cell, the same overall, but we'll be able to get a lot more sort of power out of it and don't have these sort of, shaded IV curves in this case because of these mismatch losses. But not everything, not all modules looks, connected in series like that. Here we have the first solar series 7 thin film cells. So if we look at the architecture of these kinds, right, we see they have these extremely long cells, right? One cell is sort of the entire length whereas before, right, we had these discretized cells. So that means that if we even have shading at the bottom, all the different cells are going to be illuminated the same. So that means that the IV curves are going to be looking the same in this case. So kind of, that's going to be no mismatch losses in this case. So for thin films, that's actually not necessarily a reason to do backtracking because you're not going to get more power out of it, right? We would take that extra incidence angles loss because we're tilting it backwards and have the irradiance the same, uniformly, but we wouldn't have a gain from it. So most sort of thin film cells, we're not actually doing any kind of backtracking for it. So that kind of comes down to the module technology. Now here is sort of also what's become what we call half-cut, twin module, butterfly modules, split module. They kind of come in many different names. But what's unique about them is that they're half-cut cells to get the same voltage, but they kind of have two identical halves that are kind of independent, right? So we see it even looks like it's sort of physically, even though this is one module, it looks like it has, a module at the bottom and a module on the top. And when you look at sort of the stringing architecture, that's actually also what's happening. So now they kind of behave like two different ones. That means that if the bottom part here is shaded affected, it's not going to affect the shading of the top half or sort of the IV curves of the cells in the top half. So that kind of brings us to some kind of new novel tracking strategies that we could just do tracking to optimize the power of the top half of the module in case that makes sense. So here we kind of see backtracking when we're doing what's called half tracking, right? We're allowing shading in this case only of, up to 50% of the module, and then we start backtracking. So then you see you have more true tracking throughout the day here with that green curve in this case. And if you had two modules in portrait, right, we would kind of, with twin modules, you would discretize it into kind of 4 different, independent cell layouts. And that could be kind of, 3 different cutoffs that you could do backtracking on that. So still not kind of a clear verdict on how to do that and how much we can actually gain from that, but there's certainly a potential to investigate. And some studies are claiming that you can be getting, maybe a percentage at least out of sort of tracking strategies like these. Right. So just to sum up a little bit, the conventional wisdom, right, is if you have silicon modules, you would do backtracking, and thin film, then you don't backtrack because of those long cells in this case. But some of the new wisdom that we kind of investigated and from these studies also coming out of that report that Josh was talking about, of course, if you have these full cell modules, right, we still backtrack. But if we have these full cells 2 in portrait, then we could backtrack half of it I was mentioning. Still not completely clear if that actually has overall energy benefits. And even going for thin films, maybe they also should be backtracking in terms of sort of life extension of these modules. And then we have these half-cut cells, which essentially acts as 2 in portrait, and there is some potential for energy gains, right? It's kind of, it's the increased angle of incidence loss is going to be outweighed by that benefit in terms of the better IV curves in that case. That's just some kind of considerations that backtracking isn't just backtracking. It becomes kind of, technological dependent and the layout of the cells even. All right. Some of the most work that we've really been doing is when it comes to uneven terrain, right? So backtracking, at least the normal ones was, kind of designed, the algorithm was derived from having a flat terrain. But that's not really the case, at least, especially in the last 5 years. All the nice sites have sort of been taking, right? So we're getting into these, slopes of 5 degrees or whatnot, as we see that here. So that means in this case here, for this middle one here, if you're using backtracking, the normal standard flat backtracking, you're either going to be backtracking too much or you'll be backtracking too little, depending on what slope, what direction that faces. So that needs to be taken into account, and we actually have good algorithms for doing that when we have this sort of uniform slopes. So here is just an example of like correct backtracking on slope terrains. And most PV modeling tools are actually able to solve that now when you have these nice monotone slopes. But again, monotone slopes is not necessarily the case, right? I mean, here we have an example where you have this more rolling terrain. And then we're back in trouble again because most softwares cannot really do that at the current stage. So Kevin and I kind of derived some new algorithms, kind of extending those, slope backtracking algorithms to be able to do that. Now, one challenge is that before, when you have a monotone slope or flat terrain, all trackers would be backtracking the same, right? So there'll be one backtracking angle. When you start going into backtracking on rolling terrain, then depending on the height and elevation changes, right, different trackers would be backtracking differently. That means instead of there being one optimal solution, now there's going to be an infinite amount of solutions. So how do you actually try and find this optimum? You could start by setting the front tracker and then saying all the trackers behind it cannot shade and do that kind of iteratively. You can start from the back and go forward. Those are just some of the most basic solutions, right? Definitely not optimal. So some things that we've been looking into is to do linear programming, which is sort of a very efficient mathematical way of solving optimization problems. And it turns out that Kevin has found a really nice way to actually formulate this backtracking, shading, and rolling terrain in terms of linear programming. So we have a paper that's being worked on right now that kind of is going to solve this. But there's still limitations. These sort of numerical algorithms are assuming that we can assume things are nice and 2D, right? So what some of the assumptions are saying is that all the rows are aligned, right? We can have rolling terrain, but that terrain can only sort of be rolling in one direction, and then it can be sloped in the other direction. We can't begin and model things where, here, right, the slope kind of varies along the tracker torque tube axis. That's still something that we can't solve with analytical problems. And then, we're looking into maybe needing to do ray tracing for that, or trying to find some kind of clever ways to extend some of these numerical ways that we have to doing that. So that's just some of the things we're doing, and just kind of an explanation of what backtracking is and why backtracking in reality is a lot more complex than just simulating. Later this afternoon, I'll be giving a tutorial on how to use PVLib for simulating bifacial systems. And when we're doing those simulations, we are, of course, also accounting for backtracking. So if you'd like to see how that's done, I think it's about 2:15 that we'll be doing that. You don't need to install anything. It's going to be running Python in your browser. And it's a good way just to kind of get started with PVLib Python if you've been wondering anything about that. I think that's it for my talk. Yeah, you're welcome to reach out if you have questions.
Thanks. Thank you, Adam, for excellent talk, and thank you, Kevin, for helping out with the slides. Kevin was supposed to come to this workshop, but unfortunately, due to our new administration and travel restrictions, that we were only allowed to send a couple people. So our next speaker is going to talk. We've talked a lot about tracking algorithms, but what's really interesting we haven't talked about is albedo enhancement, right? And so one of the questions, I mean, we saw some examples earlier today in the industry session about, trying to add materials, and we saw some pretty very positive results shown in the field. And so what we're going to hear about is a new software package library that will help kind of do those calculations. So yeah, Franco Clandestino from PV Radar will give the presentation.
Thank you very much for the introduction. So, well, in this presentation, I will focus more in our platform. So the package will be addressed in the hands-on session right after PVLib. So, right. So, well, the goal of this presentation is to show how with PV Radar we run techno-economic albedo assessment of albedo enhancers, and a little bit of, well, as an introduction of the company. So what do? PV Radar provides software solutions to help project developers achieve maximum performance and profitability, always to drive data-driven decisions. And we started by assessing the lifetime risk of new projects. So why is that? Because in general, when you have a new project, in the early design of the project, there are always some assumptions being made. So for example, I go to my PVCs, and in general, developers put, I don't know, like 2% in soiling losses, 2% in temperature or snow losses. And that's, from our point of view, a critical point that needs to be improved. With modeling and historic satellite data, we are able to estimate those losses in a very more accurate way in order to avoid finding underperformance when the power plant is in operation. Together with identifying the risks, we also propose solutions. So our platform is also able to provide cleaning cost optimization for power plants under development, once again, and also in operation. And lastly, the topic of this presentation, we evaluate the albedo improvement offered from some materials. This is our team. So we are a team of 3 co-founders, and 2 of us, we come from the solar industry, from developers, project developers. And at that time, particularly me, I was responsible for evaluating the site risks of new projects in Latin America. So we had our test facility located in the north of Chile. And we were asked a lot what were going to be the site risks of future projects located in Peru, Chile, and Colombia, and so forth. At that time, we were trying to solve this using Excel, loading tons of data. And of course, well, maybe you're familiar with those kind of problems. Dealing with a lot of data is not easy. Different sources have different units, different time resolutions, different particularities, for example, the time zone. So basically, we team up with Konstantin Pogorelov, which is our CTO, to develop the tool that we would have liked to have during that time. And of course, as being, well, focused on modeling, we try to be very close to the latest research. That's why we come with our advisors. So Professor Thomas Hamaha, Leonardo Micheli, who, well, doesn't need any special introduction, and Ben Figgis, who was a former program manager at Query. So far, we have been part of IEA PVPS and contributing to the 3 reports, particularly to the best practices for optimization of bifacial photovoltaic tracking systems. We run an example case using PV Radar, which is the one I'm going to present today. So I mentioned before that we have 2 products. The first one is the platform. So the idea of the platform is to run evaluations in under 5 minutes for any location worldwide. We source the data and everything for you. With this, we allow project developers to assess the risks of their future projects, to identify cost-effective investments, so optimal cleaning strategies, or high albedo materials, for example. And after a simulation is done, you can easily generate a comprehensive PDF report. For more advanced simulations, we offer our Python package. This is more focused for performance engineers. So with this is a way more flexible tool. And of course, the benefits are that you get access to tons of data, all of it format already, so you don't worry about any kind of problems that were happening before. You can also build your customized models in our dedicated environment, and you can fit those model parameters against your measurements on site. So jumping into our use case, how does PV Radar simulate the effect of albedo enhancers, both economic and technical? So why is PV Radar different, for example, to PVSys or other simulation tools? So as you can see, well, there are many things taking part of the simulation that needs to be, well, that are representative of each location. So for example, we start by modeling the albedo, the bifacial gain due to the albedo enhancers. So we have our view factor model that is, well, slightly described here. And we also take high resolution historic data. So in the graph, I'm showing more than 20 years of albedo data for that site. And with this, we are able to identify seasonality, year-to-year variations, rather than just putting one value as other tools. Then when we have modeled the effect of the albedo enhancer, we jump into the yield estimation, where we can very easily differentiate between the production that the monofacial power plant would have On top of that, we identify the bifacial gain associated to the natural albedo of the ground. And finally, the additional energy that comes from the product that is increasing the albedo. In this regard, we also consider environmental effects, so soiling effects, both in the module, air, and in the albedo material. And of course, albedo degradation. We already heard that that is a major topic to take into account. Finally, regarding the financial optimization, we know that placing the material all over the area is not cost effective. So that's why we allow to test different material placement configurations. So for example, here I'm presenting one rows underneath the modules with an overhang. And finally, the economic evaluation to understand whether the investment in this albedo material is profitable or not. We start, well, okay, the idea of the platform is to be able to answer the question, is the investment in this particular albedo material something profitable to my power plant or not? And we try to solve this in just in these very 7 steps. So, right, the first step is to select the location and to describe the main parameters of my power plant. So here we are talking about a power plant in Saudi Arabia, a 100 megawatt power plant that is of course bifacial with the standard PERC that is 70% of bifaciality. Right, here are some key parameters are required. So for example, the DC to AC ratio will have an impact on how much energy could be added from the extra bifacial gain. And also the module size and capacity will also have an impact on that. Then on step 3, well, I just skip because of time constraints. Step 2, which is about the layout, but in step 3, albedo improvement is we need to define what is the base case of my evaluation. So here I want to understand what are the natural conditions of albedo in my site. I have 3 options. So I have the mean daily albedo, which is basically I source 20 years of data, daily resolution data, and I come to a kind of a TMY, but it's actually a mean year. So for each year, for each day of all the 20 years, I have one mean value, and that gives me the red line in the graph. The second option is to use the average albedo, so one value that represents the entire year or the entire collection of 20 years. And finally, if the user has more inputs, they can upload their data, or they can just define one single value that represents the condition. Then we jump into the albedo enhancing material. We also need to describe the technicalities of this material. And well, to start, we allow the user to define what is the albedo generated by this material. In this case, we are sending it to 70%. And something that is interesting that I mentioned before is the albedo sheets placement. We could, in this version that is limited, we could select between the full ground coverage that is basically covering the entire area, or the regular pattern with gaps. In this case, yes, we are taking gaps. Well, we are putting the material underneath the modules, and we are also accounting for a material overhang of 0.5 meters each side. So that's the condition we are simulating. Right. After that, we can go deep into the energy gains. So here, the idea is to make a breakdown of what is my situation in terms of gain from my natural albedo conditions and the gains associated to my material. And here's something interesting is that I don't know if you're able to see it, but we have something that we call effective gains and virtual gains. Effective gains is the actual energy that we are producing, and virtual gains are those this additional energy that could be produced by the albedo increaser, but because of electrical limitations such as clipping or curtailment, for example, that energy is not being taken into account. Well, just to go to the results. So we see that we are able to calculate the theoretical monofacial yield of the power plant. After that, we identify that the bifacial gain without the product, that means associated to the natural albedo conditions, it's equal to 4.769. And on top of that, we have the benefit from the high albedo material, adding an extra 2.2%, resulting in a 6.9% of bifacial gain for this project. Maybe something to note here is that we are starting from a very convenient scenario. So the albedo conditions in Saudi Arabia are quite high. So the benefit here could be even bigger for another power plant in another location. After we have simulated the technical part of this, we need to account for the costs and the economic evaluation. So we have this simple page where we can describe the material cost. And we divide it into three main costs. The first one is the material price per square meter, the shipping price, and also the installation price that will give us a total investment depending on how much area I cover with the material. Of course, this is once again the base simulation. This could be customized for different cases. And finally, with all that information, I'm able to come with a cash flow. So in order to understand whether this is a convenient, a profitable investment or not, I can, well, I need to still enter some basic parameters of my financial planning. So what is the energy sales price? What will be the discount rate and the project lifetime of my project? And after that, I can see that for this very example, the payback time of my investment would be 9.9 years. Of course, this is a simplified scenario where we assume the albedo sheets will last the 30 years. Of course, that's something maybe not that realistic. So an improve for this simulation would be to consider that the albedo has a lifetime and needs to be replaced every 6 years, for example. Right. Well, this is something that I didn't want to show, but it's there. We are actively participating in different research-oriented events. So you'll find us in many events as well. And after that, well, I will be giving the hands-on demo. So where we will be going deep into how to use the tool and also how we can get the most out of the Python package. Thank you very much for your time.
Okay. I want to quickly see if there are any questions in the room. I have a few I've written down, but let's get to some in the room. Can you, yeah.
Thank you very much for all the presentation. My name is Ali Sohani from University of Montreal. Nicholas, thank you very much for your very nice presentation. I have a question about the placing in the module. I mean, would you think it's better to put the sensor for RTI on the edge or close to center, or by a similar logic, you put something in between? For on the module.
Can you hear me? I missed part of it. Would you say sensor on the ATI?
No. 30 for the rear tilted radians
Yeah.
for radiation on the back. Would you think it's better to put it in center? I mean, in the module scale, set in the center of module or on the edge of module, or something in between, as you say, for
Yeah,
the string?
I mean, just to try to repeat what I said it earlier, not on the edge, not on a south edge, not on an east or west edge.
No. For, okay, you put a place for an array, you select something on the halfway, right?
Yeah. So yeah, the torque tube is sort of your reference point, right? And then 100% to the east would be on the eastern edge, so halfway between the torque tube and the eastern edge.
Okay,
Usually the transverse or beams or the purlins are long enough to mount a sensor there. And yeah, it is displaced then a little bit from the plane of array, but it's
Okay,
it is sufficient. yeah.
so you put on torque tube, right? The sensor.
Can you repeat that?
You put on torque tube, right? The sensor.
Oh, yeah. The torque tube's interesting. You could put it on the torque tube. You really could put a single sensor on the torque tube near the center of the tracker.
Okay,
And you could probably live with just a single sensor there. I just think if you're trying to analyze the effects of the east and west side, you really should have two, one on the east, one on the west. Because typically for bifacial, it's the tracker side that's closer to the sky that will get more irradiance than the side closer to the ground. So if you have just one on the torque tube, that won't really show you that. But if you're sort of low on resources or trying to cut costs, you could conceivably put a single pyronometer on the bottom of the torque tube, again, near away from the north-south edge, and again, away from piles, but you could get away with that.
okay, so it would be a good representative for the effective irradiance for the whole.
Yeah, what we've seen is it's an effective approximation of the spatial average over short and long-term scales. Yeah, for really standard tracker designs, I should emphasize that. Yeah.
Okay, thank you.
But if you have two up portrait, you probably do want one, and
Yeah. I mean, my
especially if they're strung.
I'd say two is sort of the minimum.
Yeah.
I have a question to Adam. Your idea with the generalized ground profiles, height profiles, it gave me a question. If you have a flat, really actually flat surface, multiple rows, is maybe the optimal for total energy generation, not that each tracker has equal angle and you do backtracking, but that the row that is most towards the sun has a steeper angle that then decreases with the distance from the rows. Do you know if this has ever been evaluated?
I haven't seen anything like it. I guess there could be a potential for very few rows, right? But once you get over 10 rows, then edge effects and stuff like that, it doesn't have that much of an effect. But there could be stuff like that. I mean, all these sort of, closed form equations that we have are, assuming 2D and they're assuming, infinite number of rows. But right, your first row could certainly be different in that case.
Franco, I have one question to your tool. Is it also able to make a prognosis on the agriculture production? Because if you have a stripe of your plastics below the tracker and then you have the agriculture stripe, could you also make an estimate about that? Because we are here in the agri PV stuff. It's not only about increasing the PV production, it's also about agriculture production.
Right. From that point of view, that's true. I mean, the platform that we have now, we haven't yet considered agri PV. So we just treat the entire surface as a whole, but it could be done. I mean, what is shown in the platform is it's less. I mean, it's constrained compared to the back end, and we could do more flexible stuff in the back end. Yes.
We have some questions from online. There's a comment actually from Carl Berger for you, Nick, saying that they're read this. In January of 2025, within the IEC TC82 PV WG9 on support structures, they're going to work on an amendment to IEC 62817 to include new features and restart IEC 62817-1 for single axis trackers. So there may be some opportunity for some of the results in the report to make their way into standards. The
Okay.
question was, are you involved in those activities?
Oh, no, I'm aware of the amendment to 62817. It's always fun to say IEC and then 5 random numbers, but I'm following it. It seems like it's very much in early days. I think it's been approved as a work item, but I haven't seen a draft of it. But it is a very much needed revision. If you don't know, IEC 62817 is the qualification standard for trackers. I think the latest edition was from 2015 or 2017, and a lot has happened in the tracker space since then. And that standard was designed for, or intended for dual axis trackers. So I think there's a lot of work the community needs to do to standardize these tests and qualifications of tracker elements.
We also have a question for you, Madalena. I was wondering how you deal with cloud enhancement, which would lead to higher diffuse fraction and also very fast fluctuations of irradiance. Do you smooth the data in any way? And then have you thought about the spectral aspect of diffuse irradiance, which depends on cloud type? I guess.
Okay, so first part of the question, if we smooth the data anyway, anyhow. So we've done this plenty from the simulation side of work, and then we simulated the diffuse tracking strategy, taking into account the motor consumption and also smoothing down the whole profile of the trackers to avoid what I show in the slide, so to avoid this jumping back and forth. When it comes to practical implementation, at this first stage of implementation, we do not do any type of smoothing, but we are working on it and we are quite far, so we expect to implement it very soon, taking into account the weather forecast. So everything will be centered on the unit, the tracker control unit, and then the weather forecast for the next hour will be taken into account, and therefore the optimum pathway for the trackers will be computed and established. There was another part.
The other part was, have you considered the effects of spectrum, where the difference in this solar spectrum during clear sky conditions versus diffuse irradiation, and
No.
how that might impact PV performance?
Yeah, also that we address it slightly with the simulation, but then when it comes to the practical implementation, you also need to have this information. And at the moment, we are only based on the Sunto sensor, so we have no possibility to address this topic.
I guess that with this, Marco Piarro, thank you for the presentation from Iraq. With this sophisticated tracking strategy, you risk to destroy the engine of the tracker. It's not really practical to move continuously the engine in relation to the weather condition.
And and that's why weather forecast is absolutely key when it comes to advanced tracking control, because if you don't have an idea if that's just a temporary effect or if that's a more long-lasting weather condition, then you cannot really take action. Then of course the effect is just detrimental on the trackers.
Yeah, I mean, I very much agree. And I think one thing to highlight is that like forecasting is key. We don't want sensors and you need forecasting anyhow. But also, right, the gain of doing diffuse stowing is pretty small, but the penalty of, diffuse stowing when you should be tracking is pretty high, right? So it's a skewed sort of, return on investment kind of distribution. So you probably even need like probabilistic forecasting to do sort of this to be an optimal. Or even just say, right, you need like a 95% chance that it's going to be cloudy for the next 2 hours. And, weather models are pretty good at knowing if it's going to be completely cloudy or there's some kind of chance of sun. And if there's any kind of chance, you just don't do it. But if you know it's going to be completely cloudy for a full day, then you do it. And you can even, right, then you don't even track more. You can maybe even track less because you could be stowed for a full day, for example. But those are important concerns.
Exactly, that's also something I wanted to add. So there is also an advantage in diffuse tracking because I showed the example of a complete overcast day, and in that case you are like the trackers that are doing diffuse optimization are fixed at the stow position, and then you are not even tracking, so you're saving energy also because of that. So that's an additional plus on the fact that you are in a more suited position for the weather condition.
Yeah, just to add to that, as far as I'm aware, the major tracker manufacturers who are doing this diffuse stow, they have some sort of hesitancy baked into the algorithm. So yeah, we've talked about how these algorithms from the big manufacturers are oftentimes a black box. But what I've been able to discern is that you know, they don't immediately go to stow at the first sight of cloudiness. You know, there's some, you know, they are informed by some means like a probabilistic forecast or yeah, maybe it's a measurement on site. But yeah, it's there's certainly some hesitancy baked into I'd say the diffuse tracking that I've seen in what the big tracking manufacturers are advertising.
So I have a question. We've heard the two-letter acronym AI in several of these presentations, including yours. Where do you actually, I haven't seen any real, what I would call artificial intelligence applications yet. Where do you see an opportunity to utilize some of these new tools? Or do you? I mean, I'm curious if you have like specific ideas about where AI could help.
Yeah, I think AI can really enable fast computation. So especially when it comes also to uneven terrain, I mean, you end up with an insane amount of data that you need to process. So AI is really